All right, so this is going to be a little crash course in the first part of 378. It's not going to necessarily go over every minute detail of the class, but if you know everything and understand everything that we talk about today, you should be in a pretty good position. So first thing that we start off with is Bayes' rule, which we all know and love, which is that the probability of A given B equals probability of A intersect B over the probability of B. And you use this so many times in the class. The class is really just about Bayes' rule and using it in a bunch of different situations. It might be also helpful to know De Morgan's laws. De Morgan's laws is that A intersect B complement is the same thing as A complement union B complement, and it actually works the other way too. A union B complement equals A complement intersect B complement. You don't have to know those things. It's not required because honestly, for every problem, you can just divide A and B into circles in some universal set, and you can figure out these things on your own by just doing it visually and logicking it out. So if you can do that, then all you really need to know is Bayes' rule. De Morgan's laws are a little just kind of an extra thing that can help in certain situations, but you might not have to know them at all. Talking about combinations, combinations are just this n choose k formula, which is n factorial over k factorial n minus k factorial. You might see this with a c. It's the exact same thing, right? Just another way of writing the same thing, combination. Interestingly, if the combinations are where order doesn't matter, if you wanted to have where order does matter, that would actually be permutations, which would be n factorial over n minus k factorial. However, you're probably not going to use permutations ever in this class where order matters, so just forget that. You're probably just going to be using combinations. Like in the following example, let's say we have 20 villagers, and 4 of these villagers are left-handed, okay? And let's say they have this special ritual that they go through in their village. In this ritual, you have 13 of these villagers that they're going to be thrown into a pool of chocolate, and the other 7 are going to be thrown into a volcano, okay? And so we want to know 13 into chocolate, 7 into a volcano. And we want to know the probability that all 4 of the left-handed villagers are thrown into the volcano, okay? That's a very important thing to know. So how you handle these problems is you divide them into groups. Divide them into 2 groups. And you can actually do this multiple different ways, which you honestly probably should do to check your work to make sure that you get the same answer both ways. But here's one way that we can do it, because we can divide it into 2 groups. So let's divide it into 2 groups like this. Let's say, and this is the general formula. You have you have A choose B1, let's call it, right? Times not A choose B2. And that's going to be over some A plus not A choose B1 plus B2. That's the general formula that you're going to have. So to make sense of that, let's divide this into some groups right here. I'm going to erase this combinations thing and the probability stuff, honestly. Okay, so you have, let's start with the people that are left-handed. All right, so here's my left-handed group. I have 4 villagers that are left-handed, and I'm going to choose how many of them will be thrown into the volcano, which is 4, okay? 4 choose 4, and then I'm going to switch this. It's A and not A. So I'm going to switch this top one to not left-handed villagers. How many are not left-handed? That's going to be 16. And how many of them are going to be thrown into volcano? Well, there's 7 thrown into the volcano, so it's 3. Okay, so it's 4 choose 4 over 16, or times 16 choose 3, and these are going to add up. So you have 20 villagers that are left-handed or not, and 7 of them are thrown into the volcano. See how this top one changes and the bottom one is constant. I can also divide them into 2 groups like this. I could say, okay, well, let's talk about the people thrown into the volcano. Let's say 7 of them are thrown into the volcano. How many of them are left-handed? 4. Okay, so I have 7 people thrown in the volcano, 4 are left-handed, and I'm going to switch this top one. I have how many people not thrown into the volcano? 13. Okay, and how many of them are left-handed? Well, 0, right? Throw all the left-handed people in. Notice that there's only one way to choose 4 from 4, and there's only one way to choose 0 from 13. So just so you know, these are both going to end up being 1. But anyway, these are still going to add up. This is 20 people that are thrown into the volcano or not, and 4 of them are left-handed. So notice that we divided it up 2 different ways. You're going to get the same answer from both of these. Basically, the answer is less than 1%. It's like 0.007 or something like that. Okay, and so if we have all 4 people that are left-handed thrown at the volcano, we know that there's a high probability that somebody has it out for left-handed people. Okay, so that's combinations. That's the combination group problem. Let's switch to just some rules for expected value and covariance and variance, which we'll do over here. So let's say that we take the expected value of 3xy minus 2x plus 7. So 3xy minus 2x, let's do 2y. 3xy minus 2y plus 7, really doesn't matter. Okay, so if we were to take the expected value of this, we know that this is the expected value. We can distribute these actually. So expected value of 3xy plus the expected value of negative 2y plus the expected value of 7. Now the expected value of a constant, well, we expect that to just be the same constant, right? So that's just ended up being 7. We can pull these constants out with expected value. So this is 3 expected value of xy plus negative 2, so minus 2, the expected value of y plus 7. Now let's see how covariance a little bit different. Let's do covariance first. So covariance of 3xy minus 2y plus 7. We handle this a little bit differently. So we need to take the covariance of each of these terms, which means this is the covariance of 3xy and negative 2y plus the covariance of 3xy and 7 plus the covariance of negative 2y and 7. Well, the covariance of something and a constant is actually just 0, right? There is no covariance there. So that just leaves us with this, and we can actually pull these constants out one at a time from covariance. So this is going to be 3 times negative 2 times the covariance of xy and y. Okay, that's the same thing. Now for variance, finally, just give us a little more space here. So if we want to take the variance of 3xy minus 2y plus 7, that would be the same thing as the variance of 3xy plus the variance of negative 2y plus the variance of 7 plus, now we have to do all these covariances. 2 times the covariance of each of these terms. So 2 times the covariance of 3xy and negative 2y plus 2 times the covariance of 3xy and 7 plus 2 times the covariance of negative 2y and 7. Well, we already established that the covariance of something in a constant is 0, so those will actually go to 0. And the variance of a constant, well, constants don't actually vary, so that's going to be 0 too. And so we're left with these terms. And we can actually pull these constants out, and when we pull them out from variance, we will actually square them, because that's how variance works. So we'll go equals, this is 3 squared, so that's going to be 9 variance of xy, plus 4, that's negative 2 squared, so plus 4 variance of y, and then plus 2, rules for covariance, times 3 times negative 2, covariance of xy and y. So those are how the different rules between covariance and variance and expected value work, so you should know all those rules. Okay, let's go back to this this village and the volcano associated with it. This is an interesting problem. So it is said that 2% of everyone born in this village is lava-born. Okay, lava-born is somebody that can walk upon the lava and not be harmed. So this would definitely be a good thing for somebody thrown into the lava pool. So they would kind of want to know this before they were thrown into the pool to see if they would have a chance, right? So it turns out that 2% of these guys are lava-born. Their probability of being lava-born is 2%. Your probability of not being lava-born is 0.98, right? And there's a reason I'm drawing this in this form. This is called event decomposition. And event decomposition is just literally named for taking a complicated Bayes rule problem and making it visual, right? Drawing a picture with it. Do you have to do it? No, but we'll see why it's effective. Because we know that 2% of these people are lava-born. We also know that of all of the lava-borns that are born, this is interesting, actually 90% of them are left-handed. So your probability of being left-handed, given that you're a lava-born, is 90%, okay? And Obviously, the probability of not being left-handed if you're lava-born is going to be 10%. Okay, and then your probability down here for regular people, it's actually just 0.2. That's your probability of being left-handed if you're not lava-born, and then 0.8 obviously is the rest. Okay, so we notice that this times this is actually just Bayes' rule. Remember that Bayes' rule is the probability of A given B, or the probability of A given B is the probability of A intersect B over the probability of B. We can rewrite this as the probability of B times probability of A given B is the intersect. Well, we have that right here. We have the probability of one thing, probability of given right here, so this should actually be our intersect right here if we just multiply these two probabilities. So 0.9 times 0.02 gives us 0.018. 0.02 times 0.1 gives us 0.002. And so these are the intersects. This is the probability of being left-handed and a lava-born. This is the probability of being not left-handed and a lava-born. Okay, these are our intersects, and then we can multiply the rest of these. What are these probabilities? 0.28 times 0.2. I think that's 0.196, if I'm not mistaken. And this is like 784. Okay, so these are our probabilities of being left-handed and not a lava-born. This is the probability of being not left-handed and not a lava-born, which we can see is the majority of the population. Okay, so we have all our intersects, and what we actually want to know, what we're interested in, we want to know the probability that we are lava-born, or let me just say it. We want to know if we are left-handed, what's the probability that we're lava-born? I say it before I write it because we can switch these things sometimes, but the given always goes on the right side, okay? So if you're left-handed, what's the probability that you're lava-born? We write that the probability that we are lava-born given that we are left-handed, okay? Well, what do we know about this? This is going to be the probability that we are lava-born and left-handed over the probability that we're left-handed, okay? This is what we don't have. How do we find the probability that we're left-handed? Well, here's all the left-handed people that are lava-born, or here it is. Here's all the left-handed people that are not lava-born. Everybody else is not left-handed. So if we just add these up, there we go. There's all the left-handed people, right? So that's going to be 0.196 plus 0.018, which of course is 0.214. Okay, so this is the probability that we are left-handed. We just added all of them up. You see that? Everyone else is not left-handed, so that must be the probability of being left-handed. We can do the same thing with being right-handed. Probability of being right-handed, add all these up, and there you go. 0.786 of the population is right-handed. So now that we have this, we can take our intersect. All right, these are all the left-handed people that are lava-born. These are all the left-handed people total, and then whatever that number is going to give us the probability of being lava-born given that we're left-handed. And that probability, I think, is about 0.084 or something around that, right? 0.018 over 284. Yeah, that seems reasonable enough. So that you have about an 8% chance if you're left-handed of actually being lava-born, which is not maybe as high as we would like if we're going to get thrown into a pool of lava. So this is kind of an interesting question right here, and we want to keep going down this rabbit hole because we really care about these left-handed people. We don't want them to die. They care about themselves. So in this situation, they actually made a device to measure the genetics inside of your body. And what this device does is very advanced, very scientific. It measures this particle called lava chlorians in your blood. And they made a distribution of different people that have different levels of lava chlorians. Okay, so let's just say X is that you're left-handed. We'll make X 0 if you're not left-handed, and 1 if you're left-handed. And then Y is going to be the number of lava chlorians that you have. You can have 0, you can have 10, or you can have 20. That's the limitations of this device. That's just how it measures. All right, so we can actually make a joint distribution function, which we'll put in a table right here. It will be at X's. So that's not left-handed people, that's left-handed people. And we'll put the number of lava chlorians that they have. And we have some kind of distribution right here that we're going to talk about. And this distribution looks something like this. Okay, and let's do 0.1, 0.07, and 0.044. Okay, so these right here are the intersects. Okay, this is the intersect of x0 and y0. This is the intersection of x1 and y0, okay? Here's x1 and y20, okay? So these are all our intersects on our table right here, and that is our joint distribution function, which could be written out also, the probability of x, y, and then you can make some big function with all of these probabilities just in a line right here. Okay, so that's how you can write a joint distribution function. We want to get the marginal distribution functions of these. And all that means is, what's the marginal? Well, marginal distribution function of x is going to be, what's the probability of x at 0 and what's the probability of x at 1? We're just removing the y from the equation. Well, this looks like it equals 0.786. And this right here looks like it equals 0.214. Okay, so there you go. Probability of x being 1, being left-handed, and not being left-handed. So that's not very interesting. What we really care about is the marginal distribution function of y. So let's look at that. This looks like 0.76, 0.1, and what is that? 0.05. 0.76, 0.1, 0.05. Those don't look like they add up to 1, do they? Let me see. 0.75. Oh, because I'm bad at math. That's why. 0.85. That gives us, okay, there we go. That all adds up to 1. Yeah, these should add up to 1. If they don't add up to 1, then you've made a grave mistake. You've done something wrong. Okay? So this right here, we can write out as a probability, as a marginal distribution function for y. So here's our distribution function for y, and we can just write it as 0.85 if y equals 0, 0.1 if y equals 10, 0.05 if y equals 20. There you go. That's how you get a, you see that? That's how you get a marginal distribution function. Okay? But, you know what I'm really interested in? Not the marginal distribution function for the entire population. I want to know about it for left-handed people. That's what I really want to know. So, let's look at this with the lava chlorine count. So if I wanted a conditional distribution function, something like the distribution function for y, given that x is 1, or given that we're left-handed, then how would I do that? Well, I would just take, these probabilities for being left-handed, and then I would divide them by the number of left-handed people. Those would all add up to 1, wouldn't they? So let's do that. We take this divided by this, this divided by this, this divided by this, and this will give us a new conditional distribution function. And those numbers happen to work out to something around, there's some rounding errors in here. 0.47 if y equals 0, 0.33 if y equals 10, and 0.21 if y equals 20. Again, there are some rounding errors, but trust me, those all add up to 1 because they should always add up to 1. Okay, so that we know for our population of left-handed people that this is the probability. They have 0, 33% have 10, 21% have 20. That's kind of different from our marginal distribution function for the entire population. So that is a conditional distribution function. Now, finally, we are going to move away from this because we're satisfied with the results of our experiment. And we're just going to talk about some general formulas. We all know the formula for expected x. You've been doing this forever. That's 1 over n times some sum of all your x's. Oh, why did I say 10? That equals 1 to n of all of your individual x's, right? That's just an average. That's the definition of an average right there. So expected x is not very interesting. But let's talk about the formula for the variance of x, which is going to be x minus expected x times x minus expected x. You'd also see that squared. I didn't write it squared for a particular reason. I'll get there. This is the same thing as, it turns out, through a proof, to be the same thing as the expected value of x squared. I'll actually write this as x times x minus the expected value of x times the expected value of x. Okay? So that is the formula for the variance of x. The reason I wrote it that way is because the covariance of x and y happens to be x minus the expected value of x times y minus the expected value of y. That happens to be proved to be the same thing as expected value of xy minus the expected value of x expected value of y. Notice how the formulas for variance and covariance are actually the exact same formula. So that can save us some headache from memorizing things. Finally, we'll talk briefly about the correlation coefficient, which is the covariance of x and y over the standard deviation of x times the standard deviation of y. That's going to lead us into regression, which we all know the formula for a line, y equals mx plus b. In econometrics, we move the b over here, we change some symbols, and we get y equals beta naught plus beta 1 x. So these beta naught and beta 1 have ways that we can figure them out. The intercept, intuitively, we know that your average y is going to equal your slope plus, your intercept plus your slope times your average x. So we know that the formula for slope is just going to be your average y minus the slope times your average x. Okay, so that's how you get the intercept, and then the formula for slope is the covariance of x and y over the variance of x. This also could be written in a different way, which is the correlation coefficient times sigma y over sigma x. Okay, to prove that these are the same thing, I'll just put in, if you have a correlation coefficient times sigma y over sigma x, that's the same thing as sigma xy over sigma x sigma y times sigma y over sigma x. You see that the y's cancel out, and you get sigma xy over sigma squared x, which is this formula. Okay, so that is what you can use. You also have for regression we have the total sum of our squares in our regression is the same as the sum of the squared residuals plus the sum of the squares that are explained by our formula. Dividing all of this by SST, we have the sum, and moving SSE over there, we have the sum of our squared residuals equals 1 minus our explained sum of squares over our total sum of squares. In a simple regression, then in general regressions, this is called R squared. In a simple regression, it's actually the same as the correlation coefficient squared. Okay, it can be written 1 minus, there's the variance of our residuals over the variance of y. Okay, that is a review of the first part of 378. All of those things that would be good to know. If you understand all of that, then you are in a pretty good place. So